Okay, we are 3 minutes past the hour, so welcome everybody to the introduction to GPU accelerated data frames in Python. This is a series of webinars that Blazing SQL is going to be organizing on introducing Rapids, NVIDIA framework for GPU accelerated data science. Agenda for today, I'm going to give you a very brief introduction to Blazing SQL and Rapids. That's going to take less than 5 minutes. And then I'm going to hand it over to Nick Becker from NVIDIA to walk us through an introduction to QDF notebook. This is going to be the hands-on part, and we'll have some time at the very end for some Q&A. So what is Blazing SQL? Blazing SQL is a GPU-accelerated SQL engine, and it allows you to run SQL queries on GPU or QDF data frames. And you can create the tables directly from files. You can create the tables directly from files that are local to your computer or remote, like in an S3 bucket. As you can see over here, this is a very, very simple example when we read a CSV file into a QDF data frame, create a table on top of that, and then run a very simple SQL query. Blazing SQL is a SQL engine. It's not a database. So that's the distinction I want you to bear in mind. Blazing SQL is part of the Rapids ecosystem. So we add to the add the SQL parser to the Rapids ecosystem. Today, we are going to be talking about cuDF, which is a backbone of Rapids. It's a data frame that sits in memory, and all the computations that you run against cuDF run on a GPU much faster than anything that you run on a CPU. Blazing SQL adds on top of that, and it helps you to express yourself not necessarily in a pandas-like API using cuDF, but in a SQL engine. And Dask allows us to scale it up. So take it from a single machine with a single GPU to a cluster of machines. We successfully run up to 700 machines cluster using Dask, running Blazing SQL and Rapids in the past. Very quickly, this is what the software stack looks like. We have CUDA libraries at the very bottom. That goes through a QDF, C++, and storage plugins that pipe into Blazing SQL. We use Apache Calcite to parse SQL queries and then build a relational algebra to execute that through CUDA kernels. We use Dask for communication, and currently we support TCP and UCX. UCX is in experimental state. Overall, the Rapids ecosystem, it's an end-to-end accelerated GPU experience. You start through you can go through the data preparation using Dask, using Blazing SQL, using QDF, and then hand it over to QML or QGraph for model training, or hand it over to PyTorch, Cheaner, MXNet, or whatnot, if you prefer doing deep learning. All of that happens on a GPU. And we also provide cuCross filter and PyVis for visualization layer. Everything is possible. All of this is possible, and all of this fits very nicely into the whole ecosystem because everybody is using Apache Arrow. So Blazing SQL, we use Apache Arrow on a GPU, so does QDF, QML. So that makes this whole thing run very quickly, and also allows this interchangeable format to pipe through the whole experience. Very quickly, your data using Blazing SQL or using Rapids, or using QDF, can live in almost any format. It can be a CSV, it can be Parquet, it can be Orc, it can be Pandas. It can be local to your machine, or it can be remote in an S3 bucket like we do over here. Instantiating Blazing SQL is very simple. You import the Blazing context, create a Blazing context, as simple as here with all the default parameters. You can register an S3 bucket. In this particular case, we register BSQL, create a table of orders. This is coming from our benchmark that I'm gonna get to in a second. And we run some SQL query on top of that. Every single query that runs with Blazing SQL returns a QDF, and Nick is going to walk us through today how to do things with QDF later on. And once you've done the ETL part of the journey, ETL part of the data science process, you hand it over to machine learning. It can be XGBoost, it can be any model from the QML library. So how do you get started with Blazing SQL and Rapids? There's two ways. You can do open source, easy installation via Concat, or download either Rapids Docker container or Blazing SQL Docker container. Or as we are going to show you today, you can use Blazing Notebooks. This is a turnkey, pre-built, completely managed experience to get easily started with Rapids and Blazing SQL. Looks like and feels like most of the time Jupyter Lab. We can create clusters. We're going to use the free GPU instance today, but you can also have create private GPU clusters up to 64 GPUs at the moment. We are currently using T4 GPUs available on Amazon, and that's pretty much it. In order to get started with today's hands-on, I'm going to actually dock this next to okay. So I'm going to ask you to go to app.blazingsql.com. I'm going to paste that in the chat window, the instructions. If I can see them, chat, there you go. Where is this? Okay, I cannot paste it, but if you wouldn't mind going to app.blazingsql.com, I really don't like when this is happening. Sign in with your Google account. I'm going to use mine. It will start a new server for you. And then at the same time, you can navigate to GitHub, to BlazingDB. Welcome to Blazing SQL Notebooks. Let's see if we already started. We should be coming online soon. There you go. Okay. I'm gonna close most of this stuff. And we're going to get started with. So I'm gonna ask you to open a terminal. So if you click on this plus button at the top left corner, if you open the terminal, we are going to, first of all, remove this Welcome to Blazing SQL folder. The reason for that is if you log in straight, very first time, you don't really need to go through these steps. But if you had already dialed in previously to our webinars, most likely your Welcome to Blazing Notebooks folder is going to be outdated. So we are going to remove that folder. Welcome to Blazing SQL Notebooks. And we are going to take and clone this repo using the HTTPS. So we're going to do git clone and clone it into our root folder here. So everybody can have all of these information and all of the notebooks that Nick is going to go through today. So when you go into the Welcome to Blazing SQL, into webinars, you should see Rapids intro notebook over there. And with that, I am going to stop sharing my screen, and I'm going to ask Nick to start sharing his.
Thanks, Tom. I'm going to be sharing my notebook shortly. Okay, Thanks for the awesome introduction, Tom. Are you able to see the notebook that I have up right now?
Yep, we can.
Yes, I can.
Great. So as Tom mentioned, I'm going to be walking through for the next 30 or so minutes an introductory notebook to cuDF, which is the GPU data frame. And as Tom mentioned, when you run Blazing SQL queries, the result that you get on a single GPU is a cuDF data frame. On multiple GPUs, multiple nodes, it is a distributed cuDF data frame. So you might be wondering, how do I use this? What does it do for me? And where do I go from here? So today we're going to walk through the basics of how to use cuDF and just a little taste of what it's capable of. So I'm going to zoom in on my screen in a second so we can all see a little bit larger font. But before I do that, I'm going to start by looking at the left of the screen. For those of you who have used Jupyter notebooks in the past, this is probably a familiar interface. But what might not be familiar is this third option on the left of the screen where it says System Dashboards. This is not always there. It's one of the wonderful features that the community has been working on and is also available in the Blazing SQL managed service. And so I'm going to click on these GPU-specific dashboards so I can keep an eye on what's going on under the hood. I can track memory. I can track the utilization of my GPU and all sorts of other things that when I'm looking to scale up my code, that might be really important. So I want to make sure that I keep an eye on these things. So I'll put them on the side. Okay, and with that, I'm going to zoom into my notebook. If folks are unable to see it, please just holler and we can look at the chat and I'll try to make things bigger. If you have questions as well, please don't hesitate to ask questions. We'll be monitoring, the chat, and we're happy to take a moment to go over things that we're experiencing together. So with that, let's dive in. We've got our metrics on the right side that we can track memory and utilization. And we've got our first code line, which is the import. So cuDF is very similar to the most popular library in the PyData ecosystem, pandas. Pandas is a wonderful library for tabular data manipulation. It runs on the CPU. cuDF is the GPU data frame for tabular data manipulations. In this notebook, we're using cuDF version 0.17. And to begin with, as we're dealing with tabular data, there are two primary data structures in cuDF. One of them is called a series. This is like a column in a tabular data set. So if you're thinking about it like a spreadsheet, it's one column of a spreadsheet. The other data structure then, of course, that is particularly important is the spreadsheet itself, the data frame. That data frame is composed of multiple series objects. So we'll start by exploring what a series is, and then build upon that to better understand the data frame and see what we can do with both of these types of objects. So to start, we can create a series by passing in a Python list. In this case, I'm passing in a list of 4 integers. And I can create this using the cuDF series constructor. And as a result, you can see when I print column, or I just type column and hit enter in the Jupyter notebook, it gives me the nice printout where each of these 4 integers is assigned to a single row in my column, just like in pandas and just like in any other tabular data framework you might be familiar with. We can see that there are 4 rows. We can also see that this is a typed data structure. Each of these values is represented with an integer with, in this case, up to a varied number of bits. In this case, it's an int64. But there are other data structures and other data types we could have used. We could have used an int32 or a 32-bit integer. cuDF lets you do all of these things as well. We can also get a little bit different information by calling print. We can actually print the object. In this case, it gives us the same output, but sometimes when we print information, print data structures, we can get a little bit more metadata about them. In this case, it's the same. And again, I mentioned that cuDF supports multiple different types of integers, as well as floats, strings, and much more complex data types, which we'll only just touch on in this exercise and notebook today. But again, the most common formats are things like int64, int32, floats, and so on. We also might notice that this column is not just the values 10 through 13. We've got a 0, a 1, a 2. This is called the index. And we can see if we actually print this index, it's another data structure. In cuDF, like in pandas, series and data frames are indexed, and these indexes allow us to do things, whether it's manipulating data and filtering it, or any other complex task. We can use the indexes to interact with our data. We can also change our indexes. In this example, you can see I'm going to set a new index. Previously, it was 0 through 3, but of course, we don't need to leave it as it is. If I wanted to, I could change it to 5 through 8. And these indexes are very useful for complex operations. We can do filtering. We can also do things like group by aggregations and joins and much more. So that's what a cuDF series is. It's a column that has the data itself of a certain type and an index to go along with it. So data frames are the next level up. We might want to associate multiple columns together, or we might already have data that has multiple columns associated in a specific order. In the next few segments, we're going to go over building these data frames and also using them in really common ways. So to begin, we can, of course, create an empty data frame. There's nothing in it. It's just an empty data structure, which we can fill. In this case, we're going to fill it with a Python list and a NumPy array. And just like in pandas, we can create new series by using this bracket notation with the name that we want to call this column in the data frame. And now you can see as a result, we have a 2-columned data frame with a key column and a value column. And we'll use that a little bit later. We can also, though, create data frames in all sorts of ways and with other different data types. In this case, we're going to create a data frame with some timestamp data. I'm going to use the datetime library, which is part of the Python standard library. And we're just going to create an array, a NumPy array, of timestamps with a datetime64 data type. And like before, we can create a data frame. So we'll create one. And you'll see right here that this timestamp column is a timestamp. And we can actually investigate this ourselves by using etypes command. We can see that this data is typed as a datetime64. Now keep in mind, this is just one additional type of many types you can use. You can even put lists inside your columns and store a column of lists. But before we get to things like that, another really common way of creating data frames is to just pass in a dictionary. This is how you might commonly do this in pandas, or you might even want to go from a pandas data frame to a cuDF data frame. If you already have data on the CPU, such as a pandas data frame, you don't want to have to recreate that manually. So instead, you can use the from pandas API to directly convert that data into cuDF. Now, we haven't really touched on it, and it's, Tom mentioned it in the beginning about how this is all running on GPUs. But when we run this line of code, we're taking a data frame on the CPU, and we are actually transferring it to the GPU. That means this data is now in GPU memory, And of course, we've only used a little bit, but this data we've used so far is more than we had before. And if we keep doing this, we will eventually see this blue bar of memory increasing in size. So let's keep going. With our data frame on the GPU, we're ready to do many other things. We can create a bunch of series and make a whole new data frame as well, fully on the GPU. And once we have this, we can also explore the data frame itself. So we'll make a new one just as an example. We can see that by default, when we print out or display the data frame in the notebook cells, it gives us information. It gives us the row count and the number of columns. It tells us the name of the columns, and it gives us a printout of several of the rows. Not all of the rows, but in this case, it's giving us the first 5 and the last 5 rows in our data, with everything else being abbreviated for space reasons. And again, we can print this, and it will be the same without just the very pretty formatting that we've come to expect from pandas. But now we also have in QDF. If you just want to look at the first few rows, you can use the head command. Like in pandas, this will print out by default the first 5 rows, but you can choose any number of rows that you want to display by passing in that number to this head method. You can also access the columns of a data frame. df.columns is the standard notation for getting the columns of a data frame, in this case, A and B. Now we can also use this notation to change the names of the columns. We can set new names for the df.columns attribute as C and D. And once we've done that, our data frame will have new columns. And when we actually view the data frame, we'll see C and D, just like we expected. Again, we can also look at the data types as I did before. In this case, we have 2 columns of 64-bit integers, and we can change them using the asType method. We can convert them to floats or a different type integer, and we can also change them to strings if we were so inclined. Now we can also do more complex things, like we can actually look at the type of this series. As you can see, an individual column in a data frame is a series. It is a QDF series. And we can print that, and it gives us the name, in this case C, the length 100, and the data type. Like a series, all data frames have an index as well. In this case, our index goes up to 100 because we have 100 rows. And we can use this index if we want to filter the data frame. Now we can also go back to pandas. We're operating on the GPU. QDF data frames can be sent back to the CPU as pandas data frames using this toPandas method. And as you can see, when we execute this command and we take the type of this new object, we get back a pandas data frame. Now we can also work with NumPy arrays if we want. We can go directly from QDF to pandas and then go right to NumPy if that's something that's important to us. If we want to stay on the GPU, we can work with a CuPy array, where we can take our QDF data frame and convert it to a CuPy array, where CuPy is the GPU equivalent of NumPy. All of these APIs are documented. We'll share links to the documentation as well, and everything works as expected. Oh, actually, perfect. Here's the link to the API docs. And we can convert this to many other formats. One of the things we might want to do is actually persist our data. We have it in memory right now, but we might want to write it to a file system. Well, just like in pandas, QDF supports the standard APIs for writing files out. In this case, we can write to CSV files using the same API as pandas, writing dataset.csv. And as you will be able to see, I now have a dataset.csv in my Jupyter Lab directory that I'm currently running in. You can also read from CSVs. Just like in pandas, we can call read CSV with our file path and get back the same data that we had before. We can also, of course, read and write many other formats. Like in pandas, cuDF supports a wide variety of readers and writers, which are all documented at the links shown right up here at the Rapids AI documentation. And that is sort of the very high-level introduction to cuDF. With that, we're going to dive into actually sort of manipulating these data structures and using them. We've seen how they kind of work at a high level. We've seen how we can get data in and out from the file system. So let's manipulate some data. And so the cuDF API, as I mentioned, is very similar to pandas. And in fact, not only is it similar, it mirrors the pandas API as closely as possible. So almost every command you would use in cuDF is the same as the command in pandas. So for example, you can slice a data frame. You can directly grab a column with this bracket get item notation. But you can also use the dot notation, df dot column name, in this case A. Both of these work and they return the same thing. You can also select multiple columns by passing in a list. In this case, with A and B, we get both columns. We can also use this .loc locator API, just like in pandas, to select rows and columns of interest. Instead of doing just one column, we could also have passed 2 columns in that same list and get back rows with index 0 to 5 for both of those columns. We can also make new columns in an existing data frame, which we saw. This data frame has 100 rows of various values. We can add a new column by just putting it in to this same pandas notation. And now we have a DFD. We can also drop columns. We can use the DF drop API, just like you would do in pandas. You can also use del, like you would do in pandas. Then you can also remove a column without modifying the original data frame. In this case, what you can do is use the same drop API, but of course you're not doing it in place here. In general, we want to avoid in-place operations, so this is the normal API. The original data frame is ABC, but we only want B and C. It works as expected. And of course, we can also pass in a list of column names to drop. We also can handle missing data. In the real world, we usually have missing data. Data is not perfect, and it's not always exactly what we want. cuDF has a fully featured support for missing values, in this case, nulls, which are represented with this NA symbol in this printout. We can do things like fill in missing values. In this case, with the column C, we're going to fill in all missing values with the number 999. And you can see in column C, we filled in these values. We can, of course, also do this for the entire data frame, keeping in mind, though, that these values that we already filled in are no longer missing. So these don't get filled in as -1. We can also do Boolean indexing. We saw that we could use that bracket notation. Well, we can use that, like in pandas, to create a Boolean index and pass that index to our data frame. In this case, we're going to filter our data frame to only the rows in which the value in column A is equal to 3. And as a result, we get a smaller data frame with only rows that correspondingly match that Boolean index. We can also do things like sorting data. Sorting is very common, and sorting is fully supported in cuDF. By default, we can sort ascending, in this case on column D. We started with it at 100 in row 0, then 99, 98. We can sort this, and it will be by default ascending. But we can also perhaps switch this to be sorting by descending order. In this case, now sorting by C, ascending equals false. And we can keep going with the reverse order as we had before. We can also sort hierarchically with multiple columns. In this example, we're not just sorting on column A, we're sorting every value in column A with column B. So 0, 0, 0, 0. And so the ordering is lexigraphically aligned to the first two columns. And again, we can actually get even more complex if we really wanted to and change the order of ascending or descending on a per column basis. In this case, we want column A to be ascending equals false and column B to be ascending equals true. Like pandas, QDF supports a wide variety of statistical operations. In this case, we're only demonstrating a couple, but we can do things like take the sum of a column. We can take the sum of an entire data frame, which by default is going to give us the sum of every column. We can also do a wide variety of operations. There are many, many different statistical operations we can do. But some of the more common ones might be taking the mean, taking the standard deviation. We might want to take the variance. Whatever we might want, QDF supports these operations as well. Now, not everything we want to do fits into this nice existing API for us. Sometimes we have to write custom functions when we're processing data. QDF supports user-defined functions. As an example, we can use the apply map API to let us build custom functions. Now, this example is, of course, very contrived because we could just add 10 to our data frame in our column. But as an example, we can write a function that just adds 10 to every value in our column C, and we can apply map this function to column C. QDF also supports histogramming with the value counts method, like in pandas, where we can create our data and we can count the occurrences of every value in our data. In this case, every value occurs 25 times in column A. Now this makes sense because we passed 4 values, each repeated 25 times. But we could do this with column B and we would get a different result. In this case, we chose randomly between 0 and 1. We made 100 samples. And so we got roughly half zeros, half ones. We can also combine data frames and series. In pandas and QDF, the API for doing these combinations is called Concat. We're concatenating our data together. So we can create 2 data frames, and we can then concatenate our data. And we can now see that the result of this is a data frame with 200 rows and 4 columns, like before. By default, with the axis equal to 0, we concatenate row-wise. With axis equal to 1, which we'll see in a moment, how would you expect us to get the result here? Well, as you might expect, we're going to concatenate this column-wise. And as a result, we get a data frame with more columns, in this case 8, but still only 100 rows. Now, QDF also supports common processing techniques like joins, which we call merges in the sort of pandas PyData ecosystem. And you can use the merge API just like you would do in pandas. You can use it by default, and it's going to try to see if it can figure out a way to join these data frames. By default, it's going to try to join column names that appear in both. But usually we want to be more specific. We want to say join on a specific column or a specific set of columns. For example, we could do a join on column A. In this case, by default, you can see that we are doing an inner join. But we could also choose the kind of join. We could do a left join. We could do an outer join. All sorts of joins can be supported and are supported out of the box. We can also, again, as I mentioned, do these merges with multiple columns. Again, in this case, the results are going to be matching exactly what you expect. Now, there is one note in QDF. Because we're running on the GPU, we're running massively parallel under the hood because GPUs are parallel processing superstars. What that means is that in operations like merges, order is not always preserved by default. If you need to keep your data in the same order, that's okay. The merge API has a keyword to decide whether or not this data should be sorted. It defaults to false, but if you want it to be sorted, just set it to true. Again, we can keep going, and there's all sorts of different types of merges we can run. I encourage you to take a look on your own and experiment and to see what kinds of speedups you get by doing merges on the GPU relative to the CPU. Like merges, group bys also often come with a variety of different flavors. QDF supports these flavors. We can do group by aggregations on DataFrames, and we can do the common reductions. We can do all sorts of different things. The API is just like in pandas. You can see that we can call .group by, passing in a column, in this case A. We could also pass in multiple columns, of course, but the result is that we get a group by object. And with this, we can do lots of things. We can do a group by sum, and we can get the results, in this case, of the sum of every other column for each value of the column A. We could also do mean. We could also use the .ag API, which is very common in pandas. It's fully supported. And as I mentioned, we can, of course, do hierarchical group bys, where we're grouping on multiple keys as well. Another common task is OneHot Encoding. Data scientists and analysts and data engineers, we often work with data that isn't numeric and doesn't have this clear, continuous representation. It's usually discrete in many cases, such as integers or categories or whatever it might be. We can create OneHot encoded data frames using the OneHot Encoding API in QDF. In this case, we're going to do this based on column A. We're passing in some categories, and we get our results. Our data frame becomes OneHot encoded. Now, there's many ways we can do this. QDF also supports this in the same way as pandas, using the getDummies API. And it works the exact same way, just like in pandas. You pass in a column of interest with your data frame, and you get your result. This is just the standard way that we interact with OneHot encoding in QDF, just like in pandas. So with that, we've gone through a variety of the high-level things we can do with QDF. Before we conclude, I want to mention a couple of things that we haven't talked about, but are very useful because of the same experience you can get in QDF within pandas. As we can see in this data frame, we only have numeric data, but we might want to operate with string data. Maybe our data set is very natural language heavy. Maybe we're dealing with categories, or we're dealing with free text fields. So we can fully handle that in QDF. And as an example of what we can do, I'm just going to quickly do a 2-minute demonstration where this series has only 2 strings in it, hello world. We can do things like use the .str API. This is just like in pandas, the string methods. It is the bridge to an entire fleet of string processing capabilities that run fully on the GPU and at blazing speed. So we can do things like call upper to turn everything into uppercase. We can call title to make it capitalized in the first letter. We can do all sorts of things. We can string split. In this case, if we call it naively, it'll split on white space. So it'll split at the end, and we just get one element. But maybe we could split on the O and get all things like this. And you can see here that we now have a column of D-type list. Again, I mentioned it in the beginning. cuDF supports these very complicated data structures inside of columns. And this is just a taste of what's possible. We can also do things, regular expressions. The cuDF regular expression engine, again, is fully on the GPU. It's accelerated. It is the same API as in pandas, and you can run your regular expressions entirely on GPUs. So with that, it's been about 35 to 40 minutes. I hope you've enjoyed this introduction to cuDF. There's a few links at the bottom of this notebook. They link out to the rapids.ai website, to the GitHub organization, where you can join the discussion, file feature requests, you can contribute if that's something you're interested in doing, and you can see all the development work that we do as it happens. There's also blogs that we regularly post on. We post on the NVIDIA blog, we have a Rapids blog that has best practices, new features, and in-depth discussions around the new functionality that's joining the Rapids and Blazing ecosystem every day. So I hope this has been informative. I look forward to hearing about what everyone does with cuDF and with Blazing SQL in their own work. If we have any questions, please feel free to shout them out, Tom or Lou.
Thanks, Nick. So this was really, really cool, and I do appreciate you taking the time to spend it, and present this to us. That's really awesome. So thanks for that. We had a couple of questions while you were talking, and I tried to answer some of them, but one that I'm not really, I just wing it, was does cuDF support a diagonal sort? Like if you have a matrix where you have PCA components in a matrix, can you sort across the diagonal of that matrix? My answer was, okay, well, you can do iloc, extract the diagonal, and then sort the values that way, but perhaps you have a better answer.
Yeah, I mean, that's a great question. So it actually brings up a really, really good part of this ecosystem, which I only barely touched on. This ecosystem is not just Blazing SQL, cuDF. As Tom mentioned in the beginning, there's cuML for machine learning, there's cuGraph. There's also cuPy, which is part of this GPU PyData ecosystem. So when you're doing operations that are fundamentally array-oriented, things like singular value decomposition or any kind of matrix decomposition or things like that, the right place to do that kind of work is in cuPy. cuPy is the GPU equivalent of NumPy, and it fully interacts with cuDF and with Blazing SQL through cuDF in a way that is seamless. In fact, so seamless that if we take this data frame that we have, I hope I'm still sharing my screen, but if we take this data frame, thanks. If we have this data frame in cuDF, if we call dot values like we would do on a pandas data frame, and we'd expect a NumPy array, we actually get a cuPy array. That is the result of this. It is staying on the GPU, but it puts us into that array world. So doing things like taking the diagonal of a matrix, in this case, this is not going to be meaningful because this diagonal this is not a square matrix. It's not the same rank. So this diagonal is not useful. But sorting on the diagonal is a classic array operation, and cuDF supports the ecosystem, and you would do this in cuPy. Does that make sense? And we're happy to take more questions about this as well. And we can take this discussion to the GitHub boards, we can take it to the community pages, we can take it to the Slack groups that we're building with the community.
That was awesome. So that's much better reply than mine. Another question that I have over here is, are you planning to implement word2vec or fast text based on cuDF and Rapids? So we branching into the NLP theory, territory.
Yeah, it's a great question. This is not the right place to give a demo, but the answer is we actually have already done a lot of work on this. I'm just looking through for those who are following the screen. I've called the dir command, which is a Python built-in command that's showing me the attributes of this class, this string methods class. And actually, there's a lot of things in here that are very relevant to much more advanced NLP processing that you actually wouldn't find in pandas. So for example, things like n-grams, things like tokenization, things like edit distance, reversing tokenization. And all of this leads me to the sort of more complex work that we did, including things like stemming and all sorts of normalization, to actually accelerate the BERT subword tokenizer. So QDF actually has an accelerated subword tokenizer, and that kind of work is a little beyond the scope of this introductory discussion. But these kinds of tasks are GPU accelerated. This work does provide significant speedups, and I would love to be I'd love to learn more about the use cases and maybe bring that discussion to Slack. And actually, you can see right here. So this is an actual GPU accelerated subword tokenizer for things like BERT NLP models.
Thanks, Nick. I am still waiting if there are any other questions. We had questions about GeoPandas-like data structures in rapid environments. I know we support QSpatial that works on top of the cuDF. I don't know if you want to just give a brief branch to QSpatial.
Sure, yeah. I won't go through it in the notebook because I think we're going to be low on time. But QSpatial is fully documented in the documentation on docs.rapids.ai. There's also a link to it in the notebooks that we just went through today. But at a high level, QSpatial is a GPU accelerated library for accelerated geospatial workflows. And it has a lot of the classic things you would want to do with GeoPandas, things like spatial joins, coordinate systems, trajectory analysis, point and polygon, and all sorts of different primitives for distance-based assessment. It's a very large surface area, so there's not time at the moment, and it's a little out of scope for this first introduction. But I highly encourage you to look at the docs.rapids.ai and look into QSpatial.
So that is actually a very, very nice branch to what's coming up. So as part of this introductory sessions to various parts of Rapids, we will be holding many, many more webinars. So the next one coming up is a cuDF for pandas users, where we're going to showcase how simple it is to take your pandas workloads and then run them on a GPU using cuDF with minimal changes to your code. And that's going to be followed by introduction to Blazing SQL. And we will be delving into QML and QSpatial and QGraph. And part of that is going to be also the introduction to clicks. Clicks is Nick mentioned there, the Subword tokenizer. Subword tokenizer is actually a function that was kind of born within the clicks part of Rapids ecosystem, and then ported to become a part of cuDF. But what it does, you can bring in your BERT trained model and use that model to tokenize the text that is held in a cuDF, in a cuDF data frame. Now, one thing that I also wanted to add is what Nick presented and what you guys followed online in the free version of the app of Blazing SQL. I showed you briefly what the private clusters look like. If you need more speed, if your data doesn't fit on a single GPU, we offer as I mentioned before, we offer clusters. You can create private clusters from anywhere between 1 to 64 GPUs and run. So 64 GPUs to give you a sense for that. It provides you with 2 terabytes I think it's 2 terabytes. My math might be off here a little bit, maybe 1 terabyte. 1 terabyte of GPU memory, so you can you can literally load the data frame that occupies 1 terabyte in the GPU memory, and then do all of these computations, literally not waiting for anything. So if that's something that would interest you, you can always ping me either on Twitter or via LinkedIn, or directly through just reach out to us through our website. And I think that actually brings us to the very end of this webinar. I wanted to really thank Nick and Mike from NVIDIA, who agreed to take some time off their busy schedules to talk to you guys and then introduce cuDF. That was awesome. In my opinion, that was really good introduction to cuDF, to show you how easy it is to get started with GPUs on and running really very fast computations on any data set. You might be thinking, like, when I was first starting working with GPUs, I was always thinking that, I've always been thinking that, you can only use GPUs for numerical computations. Like, when you train deep learning models, you have large matrices of numbers, and then GPUs are really good at crunching those. But with the introduction of, handling datetime and, datetime objects and strings on the GPU, Rapids is becoming a really quick and very easy replacements for most of the data science tools that we currently have in the PyData ecosystem. So once again, Nick, Mike, thank you very much for joining us, for taking the time. And yeah, join our Slack, follow us on Twitter, follow us on Facebook. We also, for those of you who would like to watch this again, we live stream that on YouTube, and you'll be able to go back and watch it on demand later on. But if we do not have any more questions, which I don't see to be popping up, then I think we can wrap it up for today. And thanks everyone for joining.